We're going to talk about wind this week. We covered almost all the atmospheric variables, and we're putting them together to determine how an air parcel moves. Air parcels will move around the Earth from one area to another, and how do they do that? So let's just take a look at what's going on right now with wind. If you'll notice, there's a big high pressure over much of the northeast U.S. And around that high pressure, we have wind. We talked about wind blows clockwise around high pressure. Well, if you follow it here, it's definitely a clockwise wind direction. But where's the strongest wind? The strongest winds are where the pressure gradient. We talked about pressure a lot. What causes it, how it changes. Well, where the pressure gradient is stronger, like up here over northern New England, we have 20, 25 knot of wind. Down here in the center of the high, where there's almost no pressure gradient, we have calm winds. So pressure gradient is a big influence on wind. Also notice winds are stronger over the water. Something else is impacting that. That's friction. Land has a lot more friction than water does, so the water is going to have much greater wind speeds. But you can see here, if you see the pressure gradient around the big high here, even down here in the Gulf of Mexico, we have southerly winds literally caused by that high up there. So let's look at another thing. I want to show you vertical profile of the winds. This is out in Illinois, central Illinois today. There's a cold front just a little ways south of there. So, and that cold air is right here. Right here is the top of that cold front. You can see all the east wind. You saw that high pressure? This is the backside of that high. And on it, we have light northeast winds, bringing in cooler air. However, above that, the winds shift. And notice how strong they get. Right about 200 millibars, maybe 250. They're peaking out about 105 knots, 100 knots there. That's the jet stream. That's the area of the max wind speeds moving around the world. Notice it's just below where the stratosphere begins. Here's the tropopause right here. You can see how the temperature is warm with height. So we wind up, you can see the winds increase as you go above, further up in the atmosphere. They peak out just a little bit below the tropopause. And they can change direction. When you have a front, warm air has come in above that front. We know warm air is lighter than cold air, so it lifted over that area. And right here it is where it lifted over it. And you can see the wind changes with that direction as well. Finally, I just wanted to show you, here's a 500 millibar chart. All I wanted to show you is notice the contours. Tighter the contours are together, the stronger the wind. That means the pressure gradient is greater. Also, right here, I wanted you to notice how parallel to the contours they are. Winds blow very, very parallel to the contours when we get all aloft. However, if you're down at the ground level, see them crossing the contours? It's very different. So let's talk about what causes all of this. How do we get winds? What forces control the speed and the direction of the winds? We're going to talk a little bit about the wreck of the Edmund Fitzgerald, great song, and how the winds picked up very quickly over the water and caused that ship to sink. The winds are the local motion of air measured relative to Earth's surface. In other words, if you feel a parcel of air hitting you in the face, the wind's coming into you from that direction. And remember, we always take wind direction as to where the wind has been to where it's moving. originated to your northwest, it's a northwest wind. If the origination point was to your south, it's a south wind. That's why we think of to our northwest as being Canada and cold air, to our south, more tropical. So that's why when you have those kind of winds, you're probably getting more of that air mass. In other words, the air is getting colder if you have a northwest wind. The air is getting warmer if you have a southerly wind. So, force. Force is what moves an object. Think about your car. If you apply a force, the motor starts turning over, wheels begin to turn, you are moving your car in a direction. If you're running, you're applying a force to your body. You're making it go somewhere. Force is simply the mass times acceleration. Mass, we talked about density. Mass is just another form of that. The more molecules in one area, that's the mass. The heavier those molecules are, the greater the mass. And acceleration is just how quickly you're changing speed. In other words, when you put your foot on the gas, you're accelerating, moving faster. So there are a number of forces that act on air parcels. I showed you pressure gradient. Another one is centripetal, Coriolis effect, friction, gravity. So let's get talking some about that. Pressure gradient is just the change in air pressure from one location to another. In other words, you move across the mountains in West Virginia and the pressure dropped 4 millibars and maybe you went 100 miles. Not a very big pressure gradient. However, if you went 100 miles and you dropped 15 millibars, that would be a very big pressure gradient. That would mean the winds would tend to be stronger because we try to get rid of pressure gradients. The atmosphere is always working to get rid of everything. It wants everything uniform. It wants the same temperature, the same moisture, same pressure. So anytime there's a pressure gradient, air is going to flow from high pressure to low pressure to get rid of that gradient. There was a very intense storm off of Massachusetts, New York the other week when we dumped ridiculous amounts of snow up there. But the winds reached 84 miles per hour out on Montauk Point, which is the very easternmost end of Long Island. Cape Cod also saw 84 mile an hour winds. So there was a tremendous pressure gradient out there. The pressure dropped literally 40 millibars in 24 hours, ridiculously amount. That caused that tremendous pressure gradient to develop and caused those strong winds. So pressure gradient is the main influence. The stronger the pressure gradient, the more the winds are going to blow. And you can see here, upper one pressure gradient is pretty tight. Doesn't take much to go across, several millibars. Here, fairly light pressure gradient, not a lot of wind. High pressures, in the middle of high pressure, not much pressure gradient. And yes, we're always trying to eliminate that pressure gradient. It's like a slope of air. You're skiing down the slope into the low pressure areas. Centripetal force. All right, that is located where the wind curves. So when you're going around a curve in the car, how do you keep your car going around that curve? What causes that? That's centripetal force. It literally is the force pulling you around the curve so you'll stay on that curve instead of going straight. So with that, there is centripetal force all over the atmosphere. Anytime you have high pressure or low pressure, the wind's going to blow around, and we've already talked about counterclockwise and clockwise. And that movement is the curve with centripetal force. And it's not independent force. It arises from imbalance of other forces. So Newton said that if I start an object in motion, it's never going to change. It's going to always keep moving in the same object unless a force acts on it. So that object is never changing its motion. So if I start a little piece of wind moving, air moving in one way, unless something acts on it, it's just going to keep moving straight. That action is centripetal force. It makes the air turn, in this case. Coriolis effect. Because we have a rotating Earth, we have Coriolis effect. And we're going to look at that some because it's kind of confusing. We know the Earth rotates around its axis in 24 hours. Well, think about it. At the North Pole, there's no axis. Literally, you're right there. The Earth may be rotating, but it doesn't take much to go around. If you're 1 foot over, you literally have a few feet that you're covering in 24 hours. The Earth is rotating there. However, if you're down at the equator, you have about 24,000 miles, roughly. So that means that that equator had to move a heck of a lot further than it did up at the North Pole or the South Pole. Because of that, we've created what we call our Coriolis effect. Literally, when you look at the U.S. here and the way it moved, you can see there was a tilt. It doesn't look like it did before. It starts looking this way, and then it changes the way it looks. That motion, that tilt, causes a force. In the northern hemisphere, Coriolis effect always acts to the right of the wind. In other words, if I have wind blowing out of the northwest, the Coriolis force will try to turn that wind more northerly. If I have it blowing out of the south, it'll try to turn the wind to the east. It'll be a southwest wind. That is the Coriolis effect. The Coriolis effect is the greatest the closer you get to the poles, and there is none at the equator. And you can see here all the deflection. The longer an air parcel moves, the more deflection there is. The stronger the wind, the more deflection. The weaker the wind and the less motion of an air parcel, the less Coriolis effect. Friction. Friction happens everywhere in the atmosphere. And, well, think about it this way. If you tried to move a flat object, a box, and just pushed it along a rough surface, it is hard to move that box, even if it doesn't weigh a whole lot. The reason it's hard is friction with the ground. Air has the same thing. If it is moving along a bumpy ground, air is being slowed. It has a lot of friction. If the air is moving over a smoother surface, less friction, it can move faster. Oceans, water, has less friction than land. Mountains in West Virginia, a lot more friction than over the flat land in the Midwest of the U.S. Winds are going to be stronger in the Midwest than they are over the mountains of West Virginia. And as you go up in the atmosphere, we get turbulence. When your plane is rocking all over the place sometimes, that is caused by this friction working its way up through the atmosphere. You can see friction here from the snow fence, water bubbling over the creeks. One more force, gravity. Everything on Earth is pulled toward the center of the Earth. That's gravity. And there's gravity on the moon, there's gravity on Mars, so there's gravity all over the place. But that gravity on the Earth that pulls everything down, pulls all air parcels down towards the ground. So when an air parcel is moving upwards, it's defying gravity. And there are two parts to gravity on the Earth. One part is due to the force of gravity, the attraction of molecules. The second part is the Earth rotates. And we talked about Centripetal force, well, here's a perfect example. Because the Earth rotates, there is a curve, there's a pull that's holding that air parcel on that curve. That's centripetal force acting with gravity. So gravity has two components on Earth. So there's all the different forces. And we talked a little bit about Newton's law of motion here, where it starts an object in a direction, it's going to keep moving. Now we're going to talk a little bit more about some specific wind effects. So we're going to start about, well, I told you that gravity pulls the air down, but we also talked about pressure gradient and that the atmosphere is always trying to eliminate pressure gradient. We know that the pressure is less, significantly less, the higher up you go in the atmosphere. Matter of fact, think about it. You're at the Earth surface, 150 millibars up is about 1,500 meters. Not even a mile. And the pressure has dropped 150 millibars. I drop the pressure in 150 millibars in a horizontal gradient, I got a tornado. So why isn't all the air parcels trying to shoot out away from Earth? Because gravity is balancing them. This balance, called hydrostatic equilibrium, is the pressure gradient force in the vertical pull of gravity down towards Earth. Gravity only acts in the vertical, doesn't act in any other direction. So it holds that air parcel in place. Now, if the air moves over a mountain, the air parcel is going to rise, but because of hence the way hydrostatic equilibrium is, it will rise at a constant rate. Then it will sink at a constant rate. There's no acceleration with the hydrostatic equilibrium. Another kind of wind is geostrophic wind. I showed you the winds parallel to the contours at 500 millibars. Why were they parallel to the contours? Because the winds are parallel because the pressure gradient force, the distance between each of those contours, how fast they are, and Coriolis effect balance. As an air parcel begins to move, the pressure gradient force is going to be the strongest and want to push it one way. The longer it's moving along that trajectory, the more the Coriolis effect is going to push the other way, till eventually they balance and the air parcel moves horizontally. Finally, if we add a gradient wind, we're only adding one other piece. We have the pressure gradient force, we have the Coriolis effect balanced, then become non-balanced because we add the centripetal force that unbalances everything. It causes the winds to move in a circle. Clockwise around highs, counterclockwise around lows. So gradient wind is the geostrophic wind plus the addition of centripetal force, so they move in a circle. Friction. When you get down close to the ground, friction is greater. So as that air parcel is accelerating across those isobars and being turned to the right, friction is slowing that wind speed. Because it slows the wind speed, it causes the wind speed not to be balanced with the Coriolis effect. When it's not balanced, instead of moving directly to across or even parallel, it has a little shift where it will move slightly out from a high and slightly in towards low. So the air is actually moving in together towards the middle of the low, not real strongly or whatever, but it's moving that way and moving outwards away from the high. Has major impacts of why we have the weather we have. And friction's winds does decrease as we move aloft. And here you can see the low with the winds moving inward with time. All right, because the winds do that, and We're in a fluid. The atmosphere is a fluid. When we move air apart down by the ground, air is going to come down from above it to replace it. There's a continuity of wind. In other words, what happens in one upper part of the atmosphere impacts what happens in the lower part of the atmosphere. And what happens in the bottom of the atmosphere impacts the upper part. So, horizontal divergence at the bound will pull air down, air sinks. Air sinking means it's warming, means the humidity is less. We have bright sunshine where you get some of that. That's mostly high pressure. Remember, highs, the wind tends to pull apart. Lows, the wind tend to move together. So we have the convergence of the wind at the surface. Aloft, winds tend to pull apart then because the air is rising up. We also have sea breezes or lake breezes if you're up by Lake Erie or another of the lakes. What happens is air heats over land, becomes lighter, wind begins to move in from the water to the land during the day. However, over water, there's not much friction, so the air is moving pretty quickly. Hits or gets very close to the land, friction increases, the wind slows down, convergence develops, and we wind up with air rising, and that's where you're getting possibly afternoon thunderstorms or clouds right along that sea breeze front. Wind vanes are a great way to measure the direction of winds. Here is a chart called the Beaufort scale, which shows you how strong winds are based on what's happening to the trees or structures around you. And we have different type of anemometers. And here is just monitoring the wind speed and direction. Remember, we got to know both. And all winds that we take at observations as part of ASOS are 33 feet above the ground, 10 meters up. So, hope you got a little bit out of that. Let me know if you have any questions.